Okay, so we are going to look at a functional group called carboxylic acids. And esters. So they have similarities similar to, say, alcohols and ethers, aldehydes and ketones. That's why we can group them together, but they have differences in where the functional group is positioned. So carboxylic acids, if you're in biology, you probably called this a carboxyl group. So the C double bond O OH is always found at the end of the chain. So similar to an aldehyde, they are going to be, this functional group, carboxyl, is going to be considered to be on carbon number 1. So you can see in the examples here, propanoic acid, methanoic acid, octanoic acid, they don't have ones in front of them. So same thing with an aldehyde. You can write the one, you don't have to write the one because it's understood to be at the end. When we talk about the properties, we're going to talk about them being weak acids, and they're going to be vital, very important for when we get to the acid-base section, acid-base equilibrium, the last unit for this year. So they are very valuable, very important molecules, and so they are often given the highest priority. So they will always be on carbon number 1. You don't have to worry about an aldehyde and a carboxylic acid being in the same molecule. That's not a thing. That doesn't happen. So again, I'm not going to give you something that is not practical. That doesn't happen in real life, even though technically on a paper pencil task, I could write, I guess, whatever I felt like. Okay, so you don't have to stress about which end is going to be number 1. Is it an aldehyde? Is it a carboxylic acid? It'll be one or the other. Okay, so when you name a carboxylic acid, you drop the ending and add oic acid. So we're still doing the same thing. You're going to name the parent chain, which of course will be the longest chain. Okay, so propanoic acid is 3 carbons. And it's up to you. So if you have been using the right-hand side as the end of the chain or the left-hand side, that does not matter, okay? You draw the double bond O as well as an OH. So another reason that these molecules are so important is because now they have really almost 2 functional groups. They have an O and they have an OH. It makes the molecules very, very polar, okay? So the carbon on the end here on the right-hand side has 4 bonds already, so it doesn't need any ticks. But the other 2, you have to make the carbon have 4. So it does say here, you could have it at both ends. This is really rare, but it is something you might see, especially in biochemistry, actually. So we'll just do an example that you can have the same functional group, a carboxyl at both ends, and that is pentane dioic acid, but that is really, really rare. 1, 2, 3, 4, 5. But at the same time, if it's at both ends, then who cares? You just put it on and both sides, right? So not so bad. All right, so the you try ones there, methanoic acid is only 1 carbon. You can draw the carboxyl group on the right or on the left. That doesn't matter. I'll draw that one on the left. Number 2 is condensed. So again, you can use the condensed form. Don't forget to count this carbon. So 1, 2, 3, 4. So this is bute and oic acid. Just like with aldehydes and ketones, we sort of talk about dropping the E. So we don't say butone or butyl, But so if you forget the AN here and just wrote butoic acid, I wouldn't take marks off. But it does sort of sound weird, so try to think of it like there are all single bonds. That means it's an alkane. So that's why the AN is there. Okay, octanoic acid is 8. Decide which end you would like the carboxyl group to be on. Maybe it is actually easier to draw it on the right-hand side. I don't know, but it doesn't matter. Fix my ticks here. And like I said, you can do condensed or not. I will admit your textbook often likes super condensed. So they might write something like this. Which is, I'm not going to lie, slightly annoying, but this is representing the double bond O and OH. They're just, it's really super, super duper condensed. So when you see that, then that means you have a carboxylic acid. Okay, so carboxylic acids are weak acids with distinctive odors. And distinctive odors is sort of a misleading term a bit, because it sort of implies distinctive odors like, you know, smells nice. No. So methanoic acid is the acid found that burns you in fire ants that they produce. Ethanoic acid is actually vinegar. So you think about vinegar has a characteristic odor. Some people don't like the smell of vinegar. It can be considered to be pungent. If I opened a bottle of propanoic acid, so one more carbon than vinegar, if I opened that bottle in our school, the entire bottom floor of St. John's would smell like vomit. So distinctive odors, okay, but not in a good way. Okay, so carboxylic acids have some pretty powerful properties because, like I said, it almost has sort of two interesting groups here, two functional groups. So you can have hydrogen bonding and bonding with water in basically two spots on these molecules. Okay, so we've been drawing the water one first. So I'll just do it the same. Oops, I'll continue to do that. Actually, I'm going to draw the solubility one in the bottom here, where it says solubility in water. And then make up a carboxylic acid. So you can use one of the ones from above. I could even do vinegar. Which is ethanoic acid. Okay, and then it can bond with water here. And it can bond here. It could even bond here. So you can see that the fact that there's a C double bond O and an OH gives the molecule some pretty interesting properties compared to just an alcohol or just an aldehyde or ketone. So when you have a carboxylic acid, it makes very strong hydrogen bonds. Now, is it necessary for you to compare an alcohol and a carboxylic acid? I think that's a bit beyond what we need to do, but definitely they can certainly form hydrogen bonds with themselves. So let's draw that picture. Again, I'll just stick with ethanoic acid. So I'm going to have to draw an ugly picture here. Okay, so they have very high melting and boiling points because they can form hydrogen bonds with themselves. I've tried to keep it simple here. There are plenty more O's and H's I could have drawn hydrogen bonds between, but so again, even making the idea that they have strong hydrogen bonds even more obvious. But I'll just keep my picture uncluttered here, so that you can see that they can form hydrogen bonds with themselves. And then just as always, we have this criteria here: solubility in water decreases as the number of carbons increase. So as you saw in your lab with ethanol and butanol and octanol, yes, they were all alcohols. They all could hydrogen bond with themselves, but definitely as you got more carbons, so octanol had 8 carbons, it definitely was less soluble. But unfortunately, we can't do a lab with this one because they're so stinky. So the reaction of a carboxylic acid is actually very similar to one that we've already seen before. So again, we're looking at oxidation, which is in organic reactions, we're going to treat it as making more bonds to oxygen. And again, we are going to simplify things here. So you have this funny O, okay, and that is representing an oxidizing agent. The one we used in our lab was KMNO4, that purple stuff. But we're going to keep it simple, okay? So we have an aldehyde here. Where the C double bond O is at the end. And then because carboxylic acids, their functional group is also at the end. Then only aldehydes can be oxidized to make a carboxylic acid. And that makes sense. So the extra O added in here comes from the oxidizing agent, but we are not going to stress too much about how that works. Just like with aldehydes and ketones, the reaction is going to be unbalanced, because it is a lot more complicated than the scope of our course in grade 12. You can't oxidize a ketone. Ketones have their functional group in the middle, and so, or in the interior of the chain, and not at the end. And since carboxylic acids have to be at the end, then oxidation does not occur. You could also think of this as coming from a primary alcohol only to make an oxidizing, to make an aldehyde, which then can be oxidized to make a carboxylic acid. Okay, so an ester is a very similar functional group. There's a C double bond O as well as a single bonded oxygen. So technically this is the functional group of an ester, okay? And I think it's Mr. Adams says sometimes that this kind of looks like, you know, the carbon is wearing glasses. If you kind of tilt your head, you know, ester is maybe a name for, you know, typically, traditionally, an older lady. It looks like the C's wearing glasses. I don't know. If you don't like tricks to remember things, you definitely don't need to do that. But if you were in his class, then you might have talked about that. Because esterification, making a polyester, is a very important reaction in biochemistry as well. So there's a very good chance that you have already talked about and looked at esters as a functional group and esterification as a reaction. Okay, so what we are going to eventually do, I'm just going to scroll down for a second. We are going to look at reactions of esters, and you can actually do questions where you take an ester and split it into an acid and a carboxylic, or an alcohol, sorry, and a carboxylic acid, because this reaction actually goes in both directions, forward and reverse. Or, you know, opposite, like synthesis and decomposition, or opposite reactions to each other. So the functional group and the name sort of takes on two parts. So what you can do, and if you don't like color in your note, then it's up to you. But what you can do is use one color to represent the part of the carbon chain that is attached to the single bonded oxygen. And then choose another color for the carbon chain attached to the double O. So the name really has two parts, okay? And you have to have at least one carbon on each side. So you could have one carbon connected to the C double bond O and one carbon connected to the oxygen. So the ester functional group, the C double bond O and the O, have to be on the same carbon, and it has to be in the interior of the chain. Okay, so I'm going to use my same color scheme over here. So when you have the first part of the name, it comes from, it says here the R prime group. If you would rather, it's this one here, the carbon attached to the single O. Okay. So it says R prime because it says R prime here, however long it is. So you count the number of carbons, and the ending we're going to use for that is YL. Okay, and then the other side, and you're going to see in a minute that that side comes from the carboxylic acid. So is it a little bit more important? You know, I guess so, kind of. So it gets the fancy ending. So you're going to count the number of carbons, including the C double bond O carbon, and you add the ending anoate. So if you look at this molecule here, it is condensed, but that's okay. So recognizing that the carbon with a C double bond O and an O attached to it, oops, sorry. This is the ester functional group. So when you look at a molecule, that's how you know you have an ester. And then what you look for is splitting the name. So how many carbons are connected to the single bonded oxygen, there are 2. So same rules as before. We're always counting the number of carbons. This is condensed instead of tick form. So the CH2, it means that that carbon has to have 2 hydrogens attached to it. So whether you use tick form or a condensed form like this one, then you're going to, that doesn't matter. You're still counting the number of carbons. So here we have 2 carbons. So that's F. And then you give the ending YL with the single O. And then this ending, this side, including the C double bond O. So 1, 2, 3, 4 is bute. And we give the ending anoate. I can't spell, sorry. So the full name of the ester or the convention that we use is we write the YL part first and then the anoate part second. We sort of have both here. It doesn't really matter what we do first. So when you have an ester, if you want to continue to use this idea of using a different color for each side, that's fine. It's not about left or right. Again, you can flip the chain. That doesn't matter. It's about what carbon is it, or how many carbons, what's the chain that's attached to the single O. That goes first. So 1, 2, 3, 1, 2, 3, propyl. And then the other side, 1, 2, 3, 4, 5, pentanoate. You know, again, we're sort of assuming that, or not assuming, I mean, it's a good assumption, but the ester functional group is at the end of each section of the name. So we call this carbon number 1 for the propyl part, and this would be carbon number 1 for the pentanoate part. So we don't usually write 1 propyl, 1 pentanoate, but if you did that, I would not take marks off. Okay? So as we are moving through the unit, we're getting more and more molecules with greater importance that the one is just sort of understood. Okay, so the second example here is actually, now it's been switched. So the part connected to, the chain connected to the single O is on the right-hand side. So that does not matter. It's more about what's connected to the single O and what's connected to the double O. So how many carbons are connected to the single O? 1, 2, 3, 4, which is butyl. And then 1, 2, 3, 4, butanoate. So you have to have at least 1 carbon, like this anoate part does down here. 1's okay, but you can't have just an anoate or just an ethyl part. There has to be 2 carbon chains of at least 1 carbon. So this is a pretty simple ester. It's ethyl, methanoate. And actually, the good thing here is that, sometimes if you look at the second example, butyl butanoate, sometimes it doesn't matter. They're the same, so that makes your life easier. These are actually synthetic smells. You could synthesize these in a lab. So butyl butanoate is If you think that something smells like banana, then that is because it has been synthesized, or that smell is the synthesized ester, butylbutanoate. But again, unfortunately, we could make esters in our lab, except butanoic acid, which we need to make this ester, would make the whole science department, the whole bottom of the school smell like vomit. Smells so bad. So weird, but a great example of a chemical reaction. Something that smells like vomit, you put it together with an alcohol and you get the smell of banana, which is kind of bizarre. Okay, so again, I'm going to use the same color system here. So all of the YL parts, I'm going to use blue for, and all of the green parts, I'll use for the anoate. And when you do this, because in the name you write the YL part first, then lots of people choose to start with that one. But again, you can do it right to left or left to right. That doesn't matter. Octanoate. Okay, so you can do the same thing if you have been writing out the chain and then going back and putting in the appropriate number of ticks to make sure that each carbon has 4 bonds. So the carbon that has the C double bond O is full. It's got 2 bonds to the carbon, double bond O. And the carbon has 2 bonds to the oxygen, and then a bond to the single oxygen and a bond to the rest of the carbon chain. So when you make an ester, when you draw it, just make sure that you're putting the O on the same carbon as the double bond O. So in biology, you would have called this an ester linkage. Okay, so you have linked 2 molecules together. All right, so propyl is 3, single O, and then pent is 5. Put that double bond O right next to the single O. 1, 2, 3, 4, 5. Because that makes the ester linkage. Okay, so decal is 10. That's not one that we often use, but again, we're just still following the same rules and checking that we've made the ester linkage, the ester functional group, C double bond O with an O attached as well. Okay, and then butyl and prop. Oops. And checking I've drawn the correct ester linkage. Okay, so you can see that it looks very similar to a carboxylic acid. There are the beginnings of a carboxyl group, but it is not at the end of the chain, so it's missing that OH. So then when you go down to the properties, then they cannot form hydrogen bonds with themselves. So they don't have the OH group like carboxylic acids do. Okay. And like I said, these are smells, are often esters. You can find them naturally. We could have made them in class if we weren't restricted by making the whole school smelly. And that, just like we've always seen the criteria here, they can be polar when they are small. So the thing with esters is they get pretty big pretty quick, but we still can draw in. Let's just draw a simple one here and show it interacting with water. But there is no OH in the ester itself, so it cannot form hydrogen bonding. Okay, so that is a very important difference between esters and carboxylic acids. Okay, so the reaction of an ester is actually called a esterification reaction, but again, look, there it is. Water, just as we've seen many, many times. So it's given a fancy name, but since you are producing water, you could call it condensation. That's fine as well. Either name is acceptable. I don't know what happened here. So the acid, I've been using green, so I'm gonna, actually, you know what? I'm gonna keep this general form black. So I'll just put a random alcohol, which has an OH. And then how do we get water? Because of course, something is going to lose its H and the other functional group will lose its OH, and you get HOH, which is water, and of course the ester. Okay, so let's try to sneak in a little example here. So I was using, I'm going to follow the same format that it has here. So I was using green, I think, yes, for the acid part. So the way you can do these reactions, if you have an acid compared to an alcohol, an acid has a C double bond OH, whereas an alcohol does not. It just has the OH. So that is the difference. So then when you have, let's do prop. We'll do propanoic acid. Because propanoic, because it has the C double bond O, then that side of the ester functional group, or that side of the ester linkage, comes from the acid, versus the alcohol, which has an OH. I'm going to draw it like this, just so I can make water. I'll pick methanol, okay? Methanol, OH, an alcohol, does not have a C double bond O, okay? So it is going to contribute the single O and then lose its H, and the propanoic acid or the carboxylic acid is going to give its OH but keep its double bond O to form the ester linkage. So when you drop it, I guess you could think of it, if you drop the OH, then this carbon here on the end with the C double bond O is missing a bond. Okay, let's put the O there then. Oh, look, we made an ester. Okay, and of course, don't forget, as often, we have H, OH, or if you would prefer, you can write it as H2O. So then the alcohol side of the ester comes from the single O, so that's methyl. And the double bond O side comes from the carboxylic acid. So prop and O8 in our example here. Sorry, I ran out of room. So you can, like I said, you can reverse these reactions, which is called hydrolysis. So splitting the ester using water. So actually, we'll do one right here. I'm going to use condensed form. I hope that doesn't bug anybody. Okay, so it says, I'm going to sneeze. It says draw and name the alcohol that was used to make the ester and draw and name the carboxylic acid that was used to make the ester. So you do need to be thinking about, okay, what's an alcohol? An alcohol is OH, and then a carboxylic acid, which we just learned today. So if you're not super familiar with it, that's okay, is a C double bond O and an OH. Sometimes these questions bother students because they're like, what? How do we know? Or don't you have to add water? So yes, that's basically what we're doing here. Okay, so even though the question doesn't explicitly say this is a hydrolysis reaction, we're basically splitting the ester and adding HOH. So splitting it splitting the ester functional group basically in half. Okay, so still here is the ester functional group. We are going to split it in half into the alcohol and the carboxylic acid. So again, you're looking for, and if you want to do the carboxylic acid first, it has a C double bond O. The alcohol does not. So this side is going to be the alcohol. Okay, and then the other side, including the C double bond O, will be the acid. When you do this kind of question, you do need to be careful. What I've drawn here right now, neither of these are correct. You have to make it look like an alcohol. So we need the H. So again, when you do this kind of question, I think it's part 2 on the review or maybe part 1, then you're thinking about, okay, if I split this ester with water, how would it look? Because you would never leave oxygen with just one bond, right? It doesn't work like that. It does say to name it. So make sure, if you're asked to do that, you're reading the question carefully. So there's 1, 2, 3, 4, 5 carbons. And the OH is on number 1. So I have to put the 1 there, 1 pentanol. And then when you get down to part B, then again, what I've drawn there in green is not really a carboxylic acid. So you have to pretend like we have added water, the OH from water, and now this looks like a carboxylic acid. And carboxylic acids have to be on the end, so you can write 1-ethanoic acid, but you don't have to. Okay, so that is one type of question you could be asked. I forget if it's in the homework, but it's definitely on the review worksheet. Okay, let's do one. We're going to do one that has something on the chain. Okay. Oops, sorry. I forgot to draw it. So let's, I'm going to put on a bromine. So you're just going to follow your rules as you have been using them the whole unit. Okay, so we have, and then for the ester, so this is an ester linkage. The part that's connected to the single O is named first. 1, 2, 3, 4, 5. And then the part connected to the double O is the second part. But now we have this bromine on the second part of the name. It's on the prop. It's on the 3-carbon chain. Okay, so when you write the bromine, we're going to put it in front of the propanoate part because it's on the propane side, on the 3-carbon side. It's not on the 5-carbon side. So when you write it like that, pentyl 2-bromopropanoate, then it's showing on the propanoate there is a bromine on carbon 2. Okay. So the mid-chemistry or the mid-unit review had the stuff that we did at the beginning, and then the review, the first sections on the worksheet, there's more about carboxylic acids and esters, and then tomorrow's lesson, amines and amides, for good reason, because just to get you some extra review. There are textbook questions you can do. All the solutions are posted on the board and on D2L, so you can give those a try and check your work. Okay? Help each other out. Thank you.